Okay, welcome. So this is day 3 of Prep Chemistry 2021. I clearly don't know what year it is, so it's a good start. So today, get excited. We're actually going to talk about atoms and the periodic table, which is where we start doing chemistry and applying some of the basics that we've talked about so far. But before we get into atoms, I just wanted to talk about units one more time really quick. I think yesterday I went a little too fast and confused some people, and I'm sorry about that. So I just want to go over like what I think is the most important part, which is getting from units to other units. So often you'll have a conversion factor. For example, 1 hour equals 60 minutes is one that you see every day. But this can also be, 1 kilogram is 1,000 grams. That kind of unit conversion is exactly the same. For the same reason that 2 over 2 equals 1, because 2 and 2 are the same thing. If 1 hour and 60 minutes are the same thing, then 1 hour divided by 60 minutes or 60 minutes divided by 1 hour is 1. And so we can multiply by a conversion factor without changing the actual quantity of stuff that we're representing. So yeah, that's what this says, is you take whatever quantity you have, so in this case 5 hours, and then we want to multiply by 1, but in such a way that we're changing the units that quantity of time of 5 hours is represented in. And so the units that we want to end up with are minutes, and so we want the units of hours to cancel out. So that means we want minutes on top so that they end up coming through in the end. So what we're going to do is we're going to take 5 hours times 60 minutes divided by 1 hour. So that's 1. Those hours are going to cancel out, and we're going to end up with 300 minutes. So that is the most important thing to get out of yesterday that is a skill I want you to be comfortable with. I see a hand up.
Yeah, I was kind of wondering, when you try to convert a number, let's say like meters to kilometers, right? Or kilometers, or however you want to say, you multiply. So if you're converting from a low, I guess, measurement to a high measurement, you multiply?
So you always, the way that I think about it is I find it easy to get confused if I'm like, okay, kilometers are bigger than meters, and so I want the thing to get bigger or smaller. And so what I do is I just think about the conversion factor. And so for like the example that you gave, kilometers and meters, the conversion factor is 1 kilometer equals 1,000 meters. And so if I want to convert kilometers to meters, I have kilometers that I'm starting with. And then I want either kilometers over meters or meters over kilometers. But if I want those kilometers to go away so that I end up with meters, that means I need kilometers on the bottom for those to cancel out and for me to end up with meters. So I'm going to do my number of kilometers, and I'm going to have, 1,000 meters over 1 kilometer. Those kilometers will cancel out. And so that for me is easier than trying to keep track of like, oh, if it's bigger, then I multiply. If it's smaller, then I divide. This way just always works. And so
basically just what you did at the bottom.
Say that again?
Sorry, I said so basically what you just did at the bottom, just stick to that.
Exactly. So whatever units you want to go away, put them in such a place in that ratio that they're going to cancel out. So I'm starting with hours, and I want hours to go away, so I'm going to put hours on the bottom. So I got a question in the chat that it's like multiplying 5 by 60. So if I'm converting hours to minutes, then I'm going to multiply by 60. But if I was converting minutes to hours, I would divide by 60. So I just always keep track of which units I want to keep and which units I want to go away. And so if I have hours and I'm converting them to minutes, I want hours on the bottom, so those hours will cancel out and they'll go away, and I'm left with minutes. If I was converting minutes to hours, I would take, 600 minutes times 1 hour over 60 minutes. And so I would be taking 600 minutes divided by minutes, so they cancel out. So I hope that makes sense. This is just the way that I think about it, so that I never have to remember, do I want to multiply, do I want to divide by this conversion factor? This way I can always just check that my hours cancel out. So we went over some other stuff with dimensional analysis and everything yesterday. I think that's a fun and useful trick. But this is the most important thing. So you always want whatever units you want to cancel out, such that one's on top and one's on the bottom. So in this case, I have hours here and hours on the bottom, so they're going to cancel out. So I hope that answers your questions. Okay. And if you want more practice on unit conversions than what was given on the problem set, I can write more practice problems and just email me and I'll send you even more practice problems, because I do think that converting from one set of units to another is something you're going to use over and over and over again. So by default, you're going to get practice throughout the next, year or whatever. But it's useful to go in being at least a little bit comfortable with this. So I'm happy to practice more on that. Okay. So elements and atoms, chemistry, yay. So an element is a substance composed of only one type of atom. We'll talk in a minute about how we can differentiate between different types of atom. But this is a picture of a pure block of iron metal. So iron is one of the elements that we'll talk about. And so elemental iron is just pure iron with no other kinds of atoms in there. And then atoms are the smallest particle of a given element. So atoms are kind of the fundamental building block of matter. And so I think of this kind of like your body is made of cells. And so cells are kind of the fundamental building block of, living things. And atoms are the fundamental building block of matter. But as we'll talk about in a minute, atoms are made up of even smaller stuff, but that smaller stuff won't be like characteristic of a given element. So an atom is the smallest amount of a given element. Does this make sense? So atoms are our building block. All of our reactions and everything we're going to talk about with chemistry is going to be between atoms. Okay. As always, please stop me if you have questions. So atoms are made up of even smaller things called subatomic particles. And I hate memorizing things, but sub is a prefix of atomic. So atomic means atom and sub means beneath. So it's like even lower than an atom is a subatomic particle. And there are 3 types of subatomic particles: the electron, the proton, and the neutron. And so we just denote them basically by the first letter of their name. And their charge is given here. So electrons have a charge of -1, protons have a charge of +1, and neutrons are neutral. They have a charge of 0. Just one quick note on the charge. The fundamental charge can be converted into our SI units of coulombs, but we just use this unit of fundamental charge so that we don't have to carry around 1.602 times 10 to the minus 19 coulombs for all of our calculations. And so we're just going to call the electron a charge of -1, a proton a charge of +1, and a neutron a charge of 0. And as always, I hate memorizing stuff. And so here's how I remember these names. A neutron is neutral, so it has a charge of 0. A proton has a charge of +1. Proton starts with P, it sounds like positive. And then the electron is what's left, and it has a -1 charge. I see a hand up. Go ahead.
Yeah. Will we ever have to memorize the mass or like the exact charge like the 1.602 times 10 to the negative 6/19 coulombs?
I have never had to memorize it.
Okay, thank you.
Yeah, that's the kind of thing that would be given to you on a test. So often on exams, your professors will give you like an equation sheet or a list of useful concepts. So like, what is the ideal gas constant, stuff like that. I have never memorized any of these numbers. I don't have them memorized today. I would not be able to recite them to you if they weren't on this slide.
Okay, thank you. That's helpful.
Yeah. I think I am particularly averse to memorizing stuff, but yeah, no. But what you should know is that this charge is small, which is part of why we just call it +1 - 1. You should know +1 - 1. That I think is fair to memorize. But not memorize because it makes sense, because proton is positive. So it starts with P. Okay. And then these masses, we call these the mass of the proton and the neutron an atomic mass unit. You'll notice that these aren't exactly the same, but they're about 1 atomic mass unit. And so these masses of about 1.67 times 10 to the minus 27 kilograms. Notice that is a very small number. 10 to the minus 27 is small. Those are what we call a weight of about 1 atomic mass unit. And then the mass of electron is even smaller. So that's about 5 times 10 to the minus 4 atomic mass units, or 0.0005. And so the things that I think you should know about these masses are that a proton and a neutron each weigh about 1 atomic mass unit, and an electron weighs approximately nothing. So remember when we were talking about sig figs yesterday and like the importance of precision, 1 plus 0.0005 is basically 1. So if you have some protons and neutrons and you throw some electrons in there, it's basically not going to change anything about the total mass. I see a hand. Yeah.
I don't know if I remember this correctly, but it's like in an atom or whatnot, the protons, number of protons and neutrons, like are the same.
We'll get to that in a minute. Okay. It's actually the number of protons and electrons are the same, but we'll go over that in just a minute. But for now, that's a great transition into what we're going to be doing next. But for now, I just want us to be familiar with what these different building blocks are. So just to reiterate the things that are important. An electron has a -1 charge and weighs approximately nothing. A proton has a +1 charge and weighs about 1 atomic mass unit. And a neutron is neutral, it has no charge, and it also weighs about 1 atomic mass unit. So do we feel comfortable with what these 3 little guys are? Okay, cool. I'm seeing a lot of yeses and I'm not seeing any new questions, but please stop me if you do have questions. Okay, so when we put these little building blocks together to build up an atom, the atoms will have 2 regions. The first thing is the nucleus. That is composed of protons and neutrons. So these were sort of the +1 charge and the neutral charge species that we were talking about before. The nucleus is tiny. It has a diameter of about 10 to the minus 14 meters. And then because it's composed of positively charged stuff and 0 charged stuff, it's going to have a net positive charge. And then the second region is the electron cloud, which contains only electrons. It is much bigger, still tiny, but much bigger. It has a diameter of about 10 to the minus 9 meters. And because it's made up of electrons, which are negatively charged, the whole electron cloud is going to have a negative charge. And just to kind of preview what we're going to talk about when we get to interactions later, because the nucleus is so small and in the middle, when atoms interact with each other, it's mostly just their electron clouds interacting. That's what's going to sort of hit each other and interact with each other in space. The nucleus is much smaller and compact in the middle. Okay, so this is the structure of an atom. Does anybody have any questions about this? Okay. So just to see how we're doing, which part of the atom do you think has the most mass? The nucleus or the electron cloud? Awesome, I'm seeing a lot of answers come in. I'll give you like 10 more seconds to answer what you think. Okay. Okay, I'm gonna stop the poll. So about 80% of you said nucleus and 20% of you said electron cloud. Okay. So yeah, this is just the results. Okay. So going back to that table that we showed a couple slides ago, the electron has a -1 charge and a really, really tiny mass. And the proton and the neutron have a positive and a neutral charge and have a much larger mass than the electron. So even though the electron cloud is much bigger, it takes up much more space. It's made up of tiny electrons, which don't weigh anything, and they're just really spread out and moving around. And so the nucleus is much smaller, but it weighs a lot more. So the answer is that the electron basically weighs nothing, and therefore most of the mass is in the nucleus. So just to go back, because someone asked, I think this is the slide you wanted to see. So the nucleus is protons and neutrons and is positive and tiny. The electron cloud is much bigger, it's negative, it contains only electrons. And because electrons weigh so much less than protons and neutrons, most of the mass is concentrated in the nucleus. So does anybody who thought that most of the mass was in the electron cloud have any questions, or does this make sense now? This is just it's related to density, that the nucleus is small in volume, but very, very dense. So it has most of the mass. And the electron cloud is big, but not very dense. So it has a much smaller amount of mass. So I'm going to pause here in case anybody has any questions. Okay. Please stop me if something comes up. Okay, so now we're going to talk about how to tell the difference between different elements. So what we showed on this previous slide is just kind of the general structure of all elements. Is there'll be a nucleus which has like some number of protons and neutrons, or at least protons, and some number of electrons in this electron cloud. But how can we tell the difference between one type of atom and another? So there are two numbers that are going to be really relevant, the atomic number and the mass number. So I'm going to call this example element X. So that's just like the name of it. So like hydrogen or lithium or whatever. So the atomic number we notate as Z. Again, you don't need to memorize like the letter Z. I'm just sort of using it as an example so you can see how we write it. The atomic number is equal to the number of protons. And the atomic number is unique for each element. So if you change the atomic number, that means you change how many protons you have, which means you're actually changing the identity of your element. So for example, hydrogen has 1 proton. It has an atomic number of 1. But if I change the number of protons and say now I have 2 protons, I don't have hydrogen anymore. Now I have helium. So if I tell you I have hydrogen, you know that I have 1 proton. And if I tell you that I have 1 proton, you know that it's hydrogen. So those two things are directly connected. You can't change one without changing the other. And then we have the mass number, which is the total mass of the atom. Now, like we talked about, electrons weigh nothing. So the mass number is equal to the number of protons plus the number of neutrons. Because the electrons weigh nothing, the number of electrons doesn't factor into this mass number. So as always, I really hate memorizing stuff. Are you sick of hearing me say that yet? So people tend to get like the mass number and the atomic number confused. The mass number is the mass. And if you know that electrons are tiny, then you know that the mass number must be the number of protons and neutrons. And then the other thing that confuses people, so the atomic number can't be the mass, it can't be the sum of protons and neutrons because we would call it the mass number. And some people get confused on whether it should be the number of protons or the number of neutrons. And I will justify in a minute why it should be the protons. I see a hand raised.
Yeah, for the mass number, are we adding the weights of the protons and neutrons, or just counting like the numbers that they have together?
So we're going to give the mass in atomic mass units, and a proton and a neutron each weigh 1 atomic mass unit. And so we are counting the number of protons and neutrons, and then because each of those weigh 1, we're essentially like doing a unit conversion that's just like 1 over 1. Does that answer your question?
Yeah, that makes sense.
Okay. I got a question in the chat about how to figure out the number of neutrons. You are right, but we're not there yet. So yes, but hold tight. So the mass number is the mass of the nucleus, which, because the electron cloud weighs basically nothing, that is also the mass of the atom itself, or very close to it. So this is the kind of thing that we do a lot in science, is like the electrons don't weigh actually literally nothing, but they weigh so little that their mass just doesn't matter. You might remember what I said before, the electron weighs 0.0005 atomic mass units. And so we just kind of don't think about the mass of the electron when we're thinking about the mass of the atom. So now getting to the number of electrons, in general, the atomic state of an atom is neutral. So it needs to have a total charge of 0. So what that means is neutrons are already neutral. So no matter how many neutrons we have, that's not going to change the charge. They have a charge of 0. So you're adding like the number of neutrons times 0. So it just doesn't affect the charge at all. But the protons and the electrons both affect the charge. And so protons have a charge of +1, electrons have a charge of -1. And so for the total charge to be 0, the number of protons must be the same as the number of electrons. So if you know the number of protons, you automatically know the number of electrons. They must be the same. So this atomic number Z is equal to the number of protons. So I'm just putting in equation form the things that I've been saying on the slide. So that atomic number, which we call Z, is equal to the number of protons. The mass number, A, is equal to the number of neutrons plus the number of protons, because those are the only things that weigh any real or significant amount. And then the last thing is the number of electrons must be equal to the number of protons. And so the way that we often write this is what I'm showing here. So I'll show an example in a minute with like real numbers and a real element, but we write it with the name of the element. So that'd be like hydrogen, helium, whatever is where that X is. And then the atomic number Z goes in the bottom. Sometimes people leave that out because if you know the name, if you know X, you automatically know how many protons there are. So that X and that Z give the same information, but one is in the form of a name and one is in the form of a number. And then in the top left, we put the mass number A. So I'll show you, this might become clearer with an example in a minute, but does anybody have any questions on what these numbers mean? Okay. So this is an example. So this is a lithium atom. So the abbreviation for lithium is Li. And then the 7 and the 3 are the mass number and the atomic number, like we talked about on the previous slide. So the first question I'm going to ask is, in a neutral lithium atom, so that means the charge is 0, how many protons, electrons, and neutrons are there? I want you to think about it for a minute, and then I'm going to pop up poll. So I just started the poll. Hopefully you can see it. Go ahead and answer how many protons, how many neutrons, and how many electrons do you think lithium has? I'll give you about another minute to think about it and answer this question. Okay, thank you all for answering. I'm going to end the poll and show the results. So about 85% of you think that there are 3 protons, 3 electrons, and 4 neutrons. So that's awesome. That's right. If you were confused, I'm going to go over it in a second, and I'll give you a little more practice too. But about 85% of you got it right. And yeah, I'll go over that in a minute. And then the second question here is, are there any other elements that have the same number of protons as lithium? Give you about 30 more seconds.
For all elements, is it always going to be an equal amount of protons and electrons?
Yes. So because the element is going to be neutral, the atom is going to be neutral, it needs to have a charge of 0. And so the neutron doesn't have any charge, so it doesn't factor into the charge. But the number of protons has to equal the number of electrons, because one has a charge of +1 and one has a charge of -1. So that's what we need in order for the total charge to be 0.
Okay.
Does the word atom and element mean the same thing? So I guess I am kind of using them interchangeably. An atom is one atom. There's like a nucleus and an electron cloud. An element is a type of atom. And so like we showed in this poll here, where 81% of you said no other element can have the same number of protons, and that's correct. So an element is just sort of a categorization of atom. So like I can have one atom of lithium, and lithium is an element. So I can have a whole, lithium metal. I can have like a whole chunk of lithium, and that would be elemental lithium. And it's made up of a whole bunch of lithium atoms. So I hope that makes sense. Cool. So just to go over the answers here. So first, how many protons, electrons, and neutrons are there? The atomic number is given here. It's 3. The atomic number is the number of protons in an atom. So there are 3 protons. The mass number is up here, it's 7. And 7 is the number of protons plus the number of neutrons. So that means that if there are 3 protons and 7 total protons and neutrons, then there must be 4 neutrons, because 3 plus 4 is 7. And then like we talked about, the number of electrons equals the number of protons, which equals 3. So there are 3 protons, 4 neutrons, and 3 electrons. And so going back to like, why should I care more about the number of protons than the number of neutrons? It's the electrons that interact with other atoms that it comes across in its environment. And so it's the number of electrons that really matters in properties of materials. And so the number of electrons equals the number of protons. And so the number of protons is what's really important. And that's our atomic number that defines what element we have. And so, yeah, so this is just restating that answer. And then only lithium can have 3 protons, because that is the definition of lithium. A lithium atom has 3 protons. If it had 4 protons, it would become beryllium, I think. And it would then have 4 electrons, and it would behave totally different because it has a different number of electrons. So we'll talk about like electrons and properties a little bit later, but the takeaway here is that protons define the type of atom that I have, or what element we're working with. So I'm going to have you practice with this in a minute. So does anybody have any questions before I send you into breakout rooms on how I did this? Because I'm going to make you do it again. So here are the practice problems I'm going to have you do in your groups. You might want to like take a screenshot of this or write down what elements you're going to be practicing with. And so for each of these, I want you to do exactly the same thing we just did. So for 36 chlorine, 19 fluorine, and 23 sodium, how many protons, electrons, and neutrons will one atom of these elements have? So does everybody have it written down? Are you ready for me to sort you into breakout rooms, or do you have any questions? Okay. I'm going to send you into breakout rooms. I'll give you about 8 minutes. So I'll pull you back in at about 11:25. But if you finish in 2 minutes and your group is totally done and you want to come back, feel free to do so. Okay. So I just opened the rooms. You should get an invite to the breakout room right now and go ahead and join those. If you haven't joined your breakout room yet, go ahead and accept that invitation. Let me know if you don't see it. Okay, so the rooms are closing, people are coming back in. Just going to give everybody a minute to file back in. Okay, I think just about everybody's back. Well, I think everybody's back. So I'm going to go through the solutions. Or I guess before I go through the solutions, does anybody have any conceptual questions? It seems like for at least some people, this was pretty clear, but does anybody have any questions before I go through the solutions? Okay. Awesome. So let's start with chlorine. There are 17 protons. That's what this number means. And so because there are 17 protons, there have to be 17 electrons. The mass number is 36. And so 36 minus 17 is 19. That's the number of neutrons. So we're going to do the same thing with the other elements. So the number of protons is 9. That's what this number is telling us. If an atom is neutral, then it has to have the same number of protons and electrons. So this has 9 electrons. And then the mass number is 19. 19 minus 9 is 10. So there are 10 neutrons. And then the last thing is sodium. it has 11 protons because that's what the atomic number means. If it's neutral, so it has to also have 11 electrons, and 23 minus 11 is 12. So it has 12 neutrons. So hopefully that's what everybody got. I'll give you a second to ask any questions if you have them. Okay. So, like we have talked about, chlorine, for example, if it has 17 protons, it is chlorine. Like every atom of chlorine anywhere in the world has 17 protons, because if it didn't have 17 protons, it wouldn't be chlorine. However, not every atom of chlorine will have 19 neutrons. So the 17 will always be true for chlorine, but some atoms of chlorine might have a mass number of 37 or 35, which would mean it has a different number of neutrons. So that is called an isotope. So we talked about 7 lithium before, which is lithium with 7 protons and 4 neutrons. But we can have an atom of lithium that has 3 neutrons, and so that's lithium-6. And so because these different isotopes have the same number of protons as each other, they will have the same number of electrons as each other. And so because the electron cloud is what interacts with other atoms, it'll behave typically approximately the same, because that number of electrons is what matters the most. But it will have a different number of neutrons and therefore a different mass. And so what is shown on the periodic table, which we'll talk about in a minute, is this is just an example of one of the elements on the periodic table. This element is called beryllium. It has an atomic number of 4, which means it has 4 protons. But then the mass number that's shown down here is going to be the average. And so what this means is that on average, if I pick a million random beryllium atoms that I find in the universe or in the world, the average atomic mass is going to be 9.01. And so that means that most beryllium atoms that I pick up are going to have a mass number of 9, which means they're going to have 9 minus 4 equals 5 neutrons. But some will have, maybe a mass number of 10. And so that's how this average is not exactly 9. Does this make sense? Does anybody have any questions? So to summarize, isotopes of a given element all have the same number of protons because they're the same element. But a different isotope will have a different number of neutrons. And the mass that's shown on the periodic table is the average of all of the isotopes that exist in the world. Okay. So where we get all of this information is the periodic table. So this is guaranteed in like the front or back cover of every single chemistry textbook you'll ever use. I'm going to put a link to a useful periodic table in the chat. I put it on the homework and it's in a link on the B courses page too. But all periodic tables are basically the same. So you can use this link I sent you. You can use the one from your high school chemistry textbook, whatever. They will all have pretty much the same information. So this is an example of what the periodic table looks like. It's organized by atomic number. So hydrogen has an atomic number of 1. If we go all the way across, helium has an atomic number of 2. Lithium has 3, beryllium has 4, 5, 6, 7, 8, etc. So if you know the atomic number of the element you're looking for, they're all sorted in order. That is the how the order of the periodic table is determined. And then we'll talk a little bit later about how we decided to, stretch it out and, put all these guys in the middle here. We'll talk about that later to talk about the shape. But in general, they're organized by atomic number, and they tend to be nearby with elements that act similar in practice. And again, we'll talk about that in a minute. So just as an example, magnesium here has an atomic number of 12. That means it has 12 protons. And then the average mass of all of the isotopes is 24.3. So a lot of magnesium isotopes will have 12 neutrons, but quite a few will have 13. And this is just the average of all of the isotopes by sort of prevalence, by how frequently we find them in nature. Does anyone have any questions about using the periodic table? For now, using it just to get the atomic number and the average mass of the isotopes. Okay. So as practice, you might want to open that periodic table link. We're going to talk about bonding later, but for now, I'm going to tell you that water molecules have 2 hydrogen atoms and 1 oxygen atom. So what I want you to work on in your groups is using the periodic table. On average, what is the mass of a water molecule in atomic mass units? And just keep in mind that the mass on the periodic table is given in atomic mass units. And then if each atom is in its most common isotope, how many protons, neutrons, and electrons are in one water molecule? Does anyone have any conceptual questions on how to solve this before I stick you in your breakout rooms?
Oh, give me a sec. Let me screenshot it. See it on the document.
Yeah.
On the slides.
Okay. I'm gonna open the rooms. I'll give you maybe 5 minutes, so about 11:36 or so. If I can find my mouse, okay. As always, for those of you watching this later, I'm going to pause the recording. You might want to pause the video to do this practice problem yourself, or, I'm about to probably tell you the answer, so it's up to you. Okay, so people are filing back in. How did that go? How do we feel? Just going to give 30 seconds for the rooms to finish closing and everybody to file back in.
Quick question. Does a hydrogen have a neutron?
Great question. I'll go over it in a minute. Okay, I think everybody is back. So first, I'm just gonna show you the relevant squares from the periodic table. So this is hydrogen and this is oxygen. So first, when we're looking at the mass of one hydrogen atom is 1.008 atomic mass units, and the mass of oxygen is 15.999 atomic mass units. And so there's a question in the chat about how to get the total mass. Literally all you do is you know that there's 2 hydrogen atoms and 1 oxygen atom. You know how much a hydrogen atom weighs. It weighs 1.008 and you have 2 of them. And you know how much an oxygen atom weighs. So I have 1.008 times 2. So that's my 2 hydrogen atoms. And I have 1 oxygen atom, which weighs 15.999. And so when I add that up, I get a total mass of 18.015 atomic mass units. So that is the mass of 1 water molecule. Does anybody have any questions on this?
Do we usually round up or do we just keep in the 0.999?
It depends. So I'm just, for now, I'm leaving all the decimal points just to be clear that when we're using the average. But 15.999 is basically 16. And so if you use a molecular weight of, we'll talk about molecular weight in a minute, but if you're solving a problem and you need this weight and you use 18, it's about the same, right? So rounding is totally fine. I'm just trying to show you that on average, the weight is a little over 18, but it is totally okay to round. So yeah, 18.015 is about 18. And then the second part is about the same as what we were doing in our previous practice. So first we need to figure out how many protons, neutrons, and electrons are in each hydrogen atom and each oxygen atom. So hydrogen has 1 proton. That's what this atomic number means. And then this was a question that somebody asked. It's a good question. On average, there are no neutrons at all. So the mass is 1 and there's 1 proton. That means that normally in a hydrogen atom, there are no neutrons at all. But sometimes there's 2 or even 3. And there's just a few of those atoms out there that have 2 and 3. And so the average is a little bit over 1. Does that make sense? Okay. And then because there's 1 proton, there's going to be 1 electron. And then for oxygen, the atomic number is 8. The most common isotope clearly has a mass of 16 because 15.999 is basically 16. And so the most common isotope of oxygen has a mass of 16, and 16 total minus 8 protons means there's 8 neutrons. And then because there are 8 protons, there must be 8 electrons too. How do we feel about that? Any questions on just that part of dealing with isotopes? So just to go back to the question about rounding, in this case, almost every oxygen atom is 16. And so if you used 16 instead of 15.999, basically nothing would change. But if we go back to magnesium, magnesium has an average mass of 24.3. So yeah, the most common isotope is 24, but there's a lot of other isotopes such that the average is pretty different from 24. And so if you use 24 instead of 24.3, that's a pretty significant change. In this case, the most common isotope is like far and away the most common isotope. And if you assume that that is the only isotope, not much would change. So I hope that clarifies that a little bit. So when we're figuring out the total number of protons, neutrons, and electrons, we just have to add up the protons, neutrons, and electrons in our relevant atoms. So we have 2 hydrogen atoms and 1 oxygen atom. So our total number of protons is 1 proton per hydrogen atom, and we have 2 of them, plus 8 protons in our oxygen atom. So that's 10. Our neutrons, we have 2 hydrogen atoms, but each of those has 0 neutrons. So this isn't going to factor in at all. And then 8 neutrons from our oxygen. So we have a total of 8 neutrons. And one check here that we did everything right is 10 plus 8 is 18. And that's the mass that we got up here. So in this case, we're totally rounding and we're assuming our most common isotope is the only isotope. So we're going to get exactly 18. But when we take into account those rare other isotopes, we're going to get 18.015. But if we found that we got 18.015 here and like 30 down here, we clearly made a mistake. And then the last thing is the number of electrons. So there's 2 hydrogen atoms with 1 electron each and 8 electrons in the oxygen atom. So that's a total of 10. Another way of getting to 10 is there has to be the same number of electrons as protons, given that our molecule is neutral. Does anybody have any questions on this? This is super important. I think it's really important to be able to practice using the periodic table and getting these numbers. They'll have more practice on the problem set, but I think this is a really important skill. So if you have any questions, either ask them now or stay after class, or as you're doing the problem set, you can go to office hours, anything like that. But I think I'd really like you guys to get comfortable with this if you're not already, and I'm happy to help. Okay. So the periodic table organizes these elements, first of all, in order by atomic number, as we've talked about. But we also have different names for the rows and the columns. So the vertical columns are called groups. So this, for example, is group 1. And elements in a group tend to behave pretty similarly to each other. And then the rows are called periods. There's less in common across a row than there is across a group. But just so you've kind of heard these words before, the vertical columns are called groups and the rows across are called periods. So the main group elements are these ones that I'm covering in blue here. These are the ones that we're going to spend basically all of the rest of the class talking about. These are the main group elements. These ones in the middle are called transition metals. And then these ones down here that actually sometimes you'll see the periodic table even more stretched out with this orange row stuck down here. These are called the inner transition metals, or the lanthanides and actinides, because they start with those 2 elements over here. We're basically not going to talk about these guys again. They're pretty rare. They're important in some applications, but we can learn a lot about the basics of chemistry just by focusing on the main group elements. But I want you guys to at least have, seen these before and know where they are on the table. And like I said, the periodic table sorts elements by properties, more or less. And so the ones on the left are metal. So metals conduct electricity and are lustrous. That means they're shiny. They're malleable, which means, you can like bend and shape them. And they're ductile, which kind of means that with some amount of effort, you can shape them into a wire. Non-metals don't conduct electricity and are not malleable or ductile. So think about, oxygen. At room temperature, oxygen is a gas. That's not a metal, right? And like carbon, think about, your pencil lead, right? Like it's not, doesn't feel metallic, right? So these yellow elements over here are non-metals. And then these metalloids in the middle are a little bit ambiguous. People don't even agree totally on which ones to classify as metalloids and which ones aren't. So I really don't want you to get caught up in like the precise definitions. Like some people put define these differently. But basically, they're ones that are ambiguous, and they often look like a metal, but on different conditions can behave either like a metal or a non-metal. So for example, they might be shiny and look like a metal, but really brittle and really bad at conducting electricity, for example. So like I said, I wouldn't get too caught up in, you know, what exactly are the properties of boron or whatever, but just be aware that on the left, we have metals, on the right, we have non-metals, and then somewhere in the middle, we kind of transition between the two of them with some elements that are ambiguous. But I think the most important thing that I want you to get out of today is I want you to be able to look at a periodic table, and if I ask you, you know, go find sulfur, tell me how many protons, neutrons, and electrons a neutral sulfur atom has, I want you to be able to do that. So does anyone have any questions on that skill? And then also remembering that the protons and neutrons are in the core or the nucleus, and the electrons are floating around in this big electron shell. So what we're going to talk about tomorrow is what exactly those electrons are doing, how they interact with each other, and influence our properties. So it's going to be really important for tomorrow that we know how many electrons an atom has so that we can work with it and figure out how it's going to behave. Cool. So that is all I wanted to cover today. So I'm going to stop the recording. As always, I'm going to stay after if anybody has any questions. And the answers for problem set 2 are already posted. The questions for problem set 3 are up. Okay. Thank you.